What you're about to watch is a lecture that I delivered at the Department of Computer Science and Engineering at Anna University Trichy. The topic of this lecture is the behavior of quantum systems and what makes quantum computing special. I'm Timothy Paul and I'm moving from grade 8th to 9th at Mount Zion International School in Pudukkottai. I hope that you'll find this lecture highly intellectually stimulating and enjoyable. Good day everyone, and thank you for being here today. Before we begin, I would like to thank Dr. Sendra Kumar, Dean of Anna University Trichy, for having graciously invited me here to deliver this lecture to you. His efforts were instrumental in my various other achievements, including the release of my book, A Pre-Teen Speaks on Science and Technology, which was released over 2 years ago. And of course, I would also like to thank Dr. Anna Head of the Department of Computer Science here at Anna University Trichy. I would also like to thank Dr. Rsa and Dr. Karthikeyan, Assistant Professors here at the Department of Computer Science. And I would also like to thank Dr. Jennifer. Today, I would like to illustrate a comprehensive history of our current understanding of quantum physics and the beginning, present and future of quantum computing. Now let's look at the topics that we'll be discussing today. Why quantum computing? Quantum computing pioneers, the fundamentals of quantum systems, Dirac notation or bracket notation, making a physical qubit, quantum cryptography, quantum entanglement, quantum supremacy, and the future of quantum computing, and then of course we'll be opening the floor to a Q&A session. But first, we must ask the question, why? Why do we need quantum computers when classical silicon computers are already so powerful and useful to us? Why do we spend so much money and time on quantum computing research when there doesn't seem to be any immediate need for them? To answer these questions, we would be wise to start at the very beginning of quantum computing history, that is, its roots, with the men who suggested its first uses. That is, Richard Feynman, Yuri Manin, and Paul Benioff. Now, you cannot talk about quantum mechanics or quantum computing without mention of Richard Feynman. He's a Nobel laureate and one of the greatest post-World War II era scientists. He is known for his groundbreaking work in quantum mechanics and the theory of quantum electrodynamics, for which he won his Nobel Prize. But most importantly for our purposes, he gave us the idea that a quantum computer is basically a computer that is based on the behavior of quantum systems. So he posited that this quantum computer could simulate the behavior of quantum systems better than classical computers. Now, what were the reasons for his theory? Now, he said that this is because of the limited memory resources of computers at the time. But of course, as you know, the memory resources of computers today are tens of thousands or even lakhs of times the memory resources of computers then. But then why do we still need quantum computers? That is because in the same lecture, he gave us the idea. Let me read this. Now, in the same lecture, he gave us the idea that due to the very fundamental nature of quantum computers, that being that they are based on quantum systems, they would be able to fundamentally simulate these systems better than any classical computer could, no matter how fast, no matter how many bits or teraflops of power it has. He suggested that these fundamental differences were absolutely the reason for us needing quantum computers. Now, one of the very important people in the birth of quantum computing is Yuri Manin. In his book, Computable and Uncomputable, which he wrote in 1980, he posited that quantum computers were going to be a thing in the future and that they were fundamentally necessary for us to gain a deeper understanding of quantum systems. It was the first book to be written about quantum computing. If you remember, Richard Feynman gave a lecture and this was the first book. Yuri Manin is a Russian mathematician, at the time Soviet mathematician, whose work later deviated from the field of quantum computing. But nonetheless, he is still known as one of the greatest pioneers of quantum computing, and he's known as one of the godfathers of quantum computing. Now let's look at the other pioneers. Paul Benioff. Paul Benioff was the first person to show that a quantum computer was mechanically possible. And he did so by describing a Schrodinger equation-based model of a Turing machine. Now I looked through your syllabus and I know that you looked through Schrodinger equations and you learned about Schrodinger equations, so this should be very familiar to you. And of course, Turing machine is the mathematical model of a computer. You all must know about Alan Turing. He is a World War II hero, and he worked in Britain at Bletchley Park to crack the Enigma machines that were used by Nazi Germany at the time, and his code breaking through the first primitive computers saved the lives of millions of people, millions of Allied soldiers in World War II. Now, in classical physics, the energy of an object can be anywhere in the range of 0 to infinity joules. But this is of course not the case in quantum systems, and this is because of the fundamentals of quantum systems. This is the core topic of what we are going to be learning today. What makes quantum systems special and what takes quantum mechanics apart from classical mechanics. Because some of you may be holding the wrong belief that quantum systems are basically shrunk down versions of classical systems. But this is not the case, and we're going to be learning why. First, superposition. Superposition or quantum superposition is a phenomenon observed only, and this is the operating word here, only in quantum systems. But there is also a version of classical superposition, and I want to get this out of the way so that this is not confusing when I talk about superposition down the line. Classical superposition is not the same thing as quantum superposition. Now, what is quantum superposition? Now, the topic of quantum superposition is that a quantum particle, that is either a nuclei, electron or elementary particles, all of these form quantum systems. Now, the idea of quantum superposition is that these particles can be in two states at a time. Now, I'd like to demonstrate this with you, with an analogy. Now, a coin. A coin can be in two states. That is, you see here, either heads or tails. But if I flip this coin, and while this coin is in the air, what state is it in? If this coin were a quantum particle, it would be in the state of both heads and tails at the same time, because it has not landed yet. But right now, I hold this coin between the palm of my hands. What state is it in? You can't tell until I open my hands and reveal that it's in heads. This is the fundamental idea of quantum superposition. That while this coin, just to say, this elementary particle is so called in the air, that is, its position has not been observed, its state has not been observed, it is both heads and tails in equal proportion. Now, to not risk accidentally teaching you some wrong things, I like to clarify that this coin is of course not a quantum particle and not subject to quantum behaviors. So this coin is not actually in heads or tails, it's simply spinning. So if you observe it at this point in time, it's heads up, and if you observe it just a fraction of a second later, it's tails up. But if it were a quantum system, it would be a ratio of both. Now, why am I telling you about this? Because quantum superposition is one of the fundamentals of quantum computing, because it allows quantum computers to have exponentially more power than classical computers. Now, a similar demonstration, and an iconic one, is Schrodinger's cat. I'm sure you've all learnt about Schrodinger's cat in one way or another. That is, a cat is put in a box and there is an observer observing nuclear radiation, and if this particle of nuclear radiation is in one state, the cat is killed, and if it's not, the cat is alive. But as long as the box is closed, it is in a superposition of dead and alive. So it is both dead and alive at the same time, like my coin, before it is open, before I open the palm of my hands. Now, if you've read the fine print of Schrodinger's cat's thought experiment, you are sure to know that The state of quantum superposition is exceptionally fragile, so it is very hard to maintain the state. And in the same coin analogy, I can only keep the coin in the air for so long. It can't keep floating forever. Sometime it has to land and the state of superposition will collapse. But in a quantum computer, we need a sustained state of superposition. Now let's look at how we do this. And quantum systems also have their energies quantized. Now, in classical mechanics, you've read that the energy of a system, that is the energy in a system, can be anywhere from 0 to infinity joules. So, if I throw the coin in the air, again I'm talking a lot about coins, but the coin has a certain energy to move upwards in the air. This can be 3.3 joules or 3.3537 newtons, right? But in a quantum system, this is not possible because the energy in a quantum system is quantized. But let's say that if it's quantized to have only values that are real numbers, this coin, if it were an elementary particle, it could only have energy values of 1, 2, 3, 4, 5 and nothing in between. No 1.5 joules or 3.5 joules or 3.75 joules. And I've made this graph here to show you how exactly this affects basically the calculations in a quantum system. But you may be wondering, we represent bits in a computer. As you know, bits are the very basic level of silicon computers. We represent them as 0 or 1. But how do we represent the so-called bit of a quantum computer, or the elementary particles or the quantum particles that we're using to form the quantum computer? These are called qubits, and they are represented through Dirac notation or bracket notation. It's spelled B-R-A-K-E-T. It's a way of representing qubits. Now, if I represented this coin while it was in the air as a superposition and as a qubit, I would represent it like this. And coin is equal to alpha heads plus beta tails. And this is simply something that you may want to know if you get into more of an advanced study about quantum computing, and you'll have to do mathematics to figure out the state of a quantum computer, the several bits or qubits in a quantum computer, how they interact and what system is formed out of their interaction. You'll of course need to know about Dirac notation, but I wouldn't stress too much about it if you're not going to get into an advanced study and you're simply enthusiastic about this very novel concept that I'm telling you about today. But you may be thinking, if the state of a qubit is completely random, how can it be useful to us? It is no more useful than a random number generator. Therefore, we have to introduce amplitudes into the mix. Now, what are amplitudes? Amplitude of a qubit is the possibility or the probability of observing the qubit in a certain state when it is observed. So if this coin had an amplitude of 75% heads, if once it is in the palm of my hand, it has a 75% chance of being heads, and therefore it is a useful qubit, unlike a 50-50 or a random 25-25 qubit. Now, these amplitudes also have to follow a rule. These amplitudes cannot be absolutely anything you want. Now, it must obey the normalization rule, which is alpha to the power of 2 plus beta to the power of 2 is equal to 1. And that is of course also shown in bracket notation. But of course we've been talking a lot about theoretical stuff, and you may want something more pragmatic. You may want a more pragmatic exploration of quantum computers. Are there already real quantum computers? How were they made? Of course, this is the classic mind of an engineer. So I'd like to show you how we make a physical qubit. Now, on paper, qubits are very simple mathematical objects, but when we translate it from paper into the real world, how does it pan out? Now let's see how we can make a physical qubit. First method is using superconductors. You may have learned about superconductors in many of the various lessons, but this is superconducting quantum computing. By cooling down a superconducting circuit to excess of minus 450 degrees Celsius, we can make a qubit. Superconducting qubits are the most prevalent type of qubits, and Google claimed quantum supremacy. That is, they claimed that their quantum computer using 53 qubits did something that a quantum computer that is not made out of quantum systems or a classical computer couldn't do. And we'll be of course learning about quantum supremacy more, as now we are in the more practical part. You can also use optical systems, that is linear optical quantum computing. Linear optical quantum computing uses photons as the qubit. Since photons are also elementary particles, they are also quantum particles, it uses photons as the qubit. This is possible since photons are also a quantum particle, but it's not as prevalent because photons are much harder to control and to read than, say, a nuclei or electrons or a superconducting circuit. But you may be wondering, even more pragmatically, after we've made a physical qubit, what can I do with this physical qubit that a bit cannot? Let's look at quantum cryptography. Now, quantum cryptography, as it says here, provides us new ways to improve classical security, or as you may know, encryption, and also provides us new ways to break it. And in the future, quantum cryptography may be the main form of encryption. As you may have studied different encryption protocols through the 1990s, there was RSA, nowadays we have 256-bit SSL encryption, and then of course we have bigger and bigger encryption as faster computers come about. But in the future, I believe that quantum cryptography may be exclusively used, meaning only quantum cryptography is used. Now let's look at encryption or classical security. Encryption works based on the sender and receiver of the encrypted information using a secret key. The ultimate weakness of classical encryption is that a secure channel is used to exchange the keys. But the paradox is that if you have a secure channel to exchange the keys, why would you need encryption to encrypt the messages in the first place? Nowadays, the most commonly used type of encryption is Rsa encryption. Rsa encryption works on the premise that modern computers or even supercomputers do not have enough processing power or memory limitations are there, so that they cannot factor prime numbers in any reasonable amount of time. Now, let's look at the antidote to this in a classical way. Public key cryptography. Public key cryptography aims to address some of the flaws of private key cryptography. Here there are two keys in the mix. There is a public key that is visible to all, and if you are using WhatsApp, you are using this type of encryption. The public key can be known by anyone and does not pose a security threat, but the private key must be kept secret. If someone wants to send a message to the holder of the private key, then they would encrypt the message with the public key that corresponds to the holder's private key, and only the receiver's private key can decrypt and read the message. Now let's look at Rsa encryption. I talked very shortly about Rsa encryption a while ago, and Rsa encryption is the most popular or most prevalent type of encryption today. It is easily broken by Peter Shor's quantum algorithm. It's also known shortly as Shor's algorithm. It is a quantum algorithm that uses quantum computers to completely break Rsa encryption. So let's say if your WhatsApp or your Signal is using an Rsa encryption, using Shor's computer algorithm, someone could within like 2 seconds decrypt your messages and read them. But Shor's algorithm has been invented 27 years ago and it has been in use since. So why are so many companies, businesses and services still using Rsa encryption? That is because quantum computers today aren't as prevalent or as easily available to pose a security threat. They are only held by few research institutions and government institutions. So, and also Shor's algorithm is not perfect, 4 bits. But if you have 8 qubits, you have the equivalent of 64 bits. And that's what makes quantum computing so special in terms of pure processing power. But if you remember what I said about Feynman before, you will know that fundamentally there are other things that set quantum computers apart from classical computers. Now let's look at exactly how this pans out with quantum supremacy. Quantum supremacy is basically an indication of when a quantum computer does something that it is impossible for a classical computer to do. And IBM and Google, two forerunners in the quantum computing space, they have tried to do this many times, and as I said before, Google has claimed quantum supremacy. They have claimed that they have already made quantum supremacy with just 53 qubits. Think about that. Your computer, even your mobile phone, has millions of bits. It has even billions of bits. But how can Google say that they have beat some of the world's fastest supercomputers with just 53 qubits? This is because of the exponential power that I talked about before. But with exponential power also comes exponential hassle. Adding more qubits is easier said than done because it introduces what we call quantum noise into the mix. As I said before, the state of quantum superposition is extremely fragile and can be broken by a simple observation. But if we have many qubits, by the very nature of quantum computers, wouldn't they interact with each other and destroy each other's superpositions? Yes, and that is why we have super cooled circuits, as I said before, superconducting circuits with minus 450 degrees Celsius temperatures just to prevent this happening and reduce the quantum noise. And adding more qubits also requires increased physical space, as you have to keep the qubits apart from each other to prevent them from accidentally interacting with each other and disturbing each other in ways that would prove very inconvenient to us. However, at this point, I would like to acknowledge that quantum computing in the future or in now is not a shiny new replacement for classical computing. It is another technology. Just because it has computing in the name doesn't mean that it is simply a new model of computing and you're going to have quantum computing phones or quantum computing desktop computers. I think that it will work in tandem or it will work with classical computers to provide or to cover for the weaknesses of classical computers, because quantum computers also have their weaknesses. They have the problems of unreliability, they also have memory issues, also you need to have a super cool circuit, and we have not found ways past that. But in the future, I believe that on your desk, 20 years from now or 30 years from now, you have a quantum computer along with your physical computer. Technologies come into and out of the frame in and out of fashion. It is the job of engineers to provide technology according to society. But depending on the technologies that engineers make for society, society is also changed by those technologies. So we must pursue every single possible avenue of development in quantum computing or in all of computer science, even if 100% of the uses of such technology is not really apparent, meaning when you start any research, even if you don't see all of the uses for it commercially or in terms of improving lives, you must pursue that avenue because you do not know what other findings you will find on the other end of that line when you research it. And I think this is the case with quantum computers. The uses of quantum computers today and the money invested in it is a reflection of the type of technological and economic landscape that we live in today. The amount of money being poured into quantum computing research, I think, will create uses for quantum computing. IBM and Google are big enough, powerful enough, and they have enough capital to create entire new fields of research and entire new fields of study to validate their investments. And this is the state of the technological landscape that you and I inhabit today. This is the cycle of Silicon Valley technology. But to me, my interest in quantum computing is forged purely out of a love for understanding. I'm curious about what quantum computing could unearth about quantum mechanics. I'm glad that more and more research is being gone out of this topic, and I hope that at least through this lecture, 100 new quantum computing researchers or at least 100 new quantum computing enthusiasts are born out of this lecture. Now, I will open the floor to questions from the audience, and I would like to once again thank you very much for your time.
Actually, first of all, congratulations that you have published your book at this young age. It's a really great achievement. I have a few questions in this quantum computers. Actually, quantum computers have a heating problem of its own. It can be used only under cool temperature. So, as a country like us, how can we use these quantum computers?
Yes, so the cooling problems of quantum computers are not due to mechanical friction or due to electrical components like in our classical computers. They need to be kept cool so that, as you know, heat causes motion in atoms and in molecular and subatomic particles. So we need to minimize this to keep this cool. And this is done, of course, through many methods like supercooled hydrogen gas and liquid nitrogen. But the uses of quantum computing are manifold. They can be used in research, and even though they are technically very big with their qubit counts, compared to classical computers, they have more power in a smaller space. So you can fit more. Let's say you want to do very memory intensive or very processing intensive research, like nowadays we have AI processing data sets that require that much power. You can fit 10 quantum computers in the space of one supercomputer, and it will be 10,000 times faster. And not only that, to model quantum systems, that is to find out how the subatomic particles work, we can use quantum computers, and they'll have an even greater exponential power to find out the behaviors of quantum particles, because they're driven by quantum particles.
And also you said that if this quantum computing is implemented in the best way, surely it will break the internet security. You know, because quantum computer can decrypt all the codes in the internet.
Yes.
So how can you provide internet security if you implement or use this quantum computers?
I think it's a very simple solution to that, because by the time that quantum computers become prevalent enough that everyone has a quantum computer, I think banks and internet companies will simply encrypt their protocols using quantum computers. So it is null and void. So it is simply not a problem it's not a security problem, because I think even now some banks are working on using quantum encryption to encrypt their banks, and even with classical computers it's hard to break, and even with quantum computers it's very hard to break that encryption. So I think it's actually good for security that these kind of risks are being posed, because if you know how security advances are made, advances in security are made only when flaws are found. So when such a big glaring flaw is found, it will only lead to more security, and I think all in all it's a good deal for us.
And last question. Actually, quantum computers are costlier.
Yes.
So due to its high price, they are not available in, for public uses. So as a middle class people like us, how can we buy this quantum computers?
I think we don't need quantum computers right now. As quantum computers, number one, they are only so expensive because they are in their early stages. Because back then, normal computers in like the 1950s, 1960s, they used to cost millions of dollars, and the people didn't need them. But as quantum computers become cheaper, more people will start buying quantum computers, and it will become even cheaper. So it's a cycle, because the economies of scale. The more things are made, the cheaper they become. So as quantum computers become cheaper, more will be made. As more will be made, they'll become cheaper. And right now we don't have many uses for them. So it's not a matter of economical availability, because we don't need them. But if there is a time when people need quantum computers, by that time they will be economical enough for us to buy. Like how we have a computer here, we may have a quantum computer here 40 years down the line. I think that's the solution. I think in the natural course of time, everything will tends to balance out. Thank you so much for your question.
So students, if you have any questions to ask Timothy, you can ask now.
Hi, good morning.
Good morning.
What's the evidence for quantum supremacy?
Yes, exactly. It's very dubious. Google claims that they did a calculation that takes only 200 seconds with a quantum computer, that would take 10,000 days with a classical computer. But of course they haven't released the research papers, or they haven't released evidence, and IBM, their rival, has claimed that no, this is not true, and they claim that with advanced supercomputing techniques, their classical computers can do the same thing in 2.5 days. So they claim that, number one, this quantum supremacy is not as impactful, and they claim that either it's false or it's not useful. And simply saying that you've achieved quantum supremacy is not useful to anyone, or it's not useful to computer science researchers, engineers, or even scientific researchers. I think we must, in the future, drop this. It's a childish competition. It's simply like it's like a bet between kindergartners about who runs faster. I think we should simply find more uses, and only 5-10 years from now we'll see any kind of useful quantum supremacy. Right now I think it's a very childish advertisement competition. Thank you so much. Very good question.
Hello.
Good morning.
What hinders implementation of
now they're mostly being implemented through superconductors, as I said before. But I think in the future, superconductors may fall out of use because as you add more and more qubits, it needs to be cooled further and further by the order of magnitude. Order of magnitude means 10 times. For each qubit that is added, you need to be cooling it 10 times. And at a certain point, it becomes unsustainable. But in early phases of quantum computing research, maybe we can keep pushing superconducting qubits. But I think in the future, eventually we'll find different ways of making physical qubits. We'll find ways of making smaller, more effective cooling solutions. And in fact, IBM, they say that by 2025, they'll have a quantum computer with over 1,000 qubits. So it's a very promising future. Of course, it's simply marketing, and you shouldn't outright believe that they definitely have 1,000 qubit. They will outright have a 1,000 qubit quantum computer, or you shouldn't believe in the virtues of 1,000 qubit quantum computers. I believe in the natural course of things. I think as time goes on, more qubits will be added. Some people will find ways to shrink down qubits, because why are we even making quantum computers in the first place? For quantum computing research. And as we make more quantum computers, we'll learn more about quantum systems, and then we can make even better quantum computers. So I think eventually it will become exponential. I'm sure you know about Moore's law. Does anyone here know about Moore's law? M-O-O-R-E, Papa Shivis, Moore's law? No? It states that every year the transistor count in computers doubles. So I believe if you look it up on your phone, you'll see a chart. So transistor counts go exponentially up, and I think at a certain point qubit counts will also follow according to Moore's law. And I think that is the current state of implementation. Right now it's very experimental phase. But I think it definitely has the potential to be implemented in a more mass way. Thank you, very good question.
Firstly, I like your presentation and the energy you brought to us while taking the seminar. And you just took us into the concept of quantum computing. But I would like to ask something from the outer view of the system or concept. We know that we have supercomputers and even this quantum computer. And supercomputers take the responsibility to solve more complex problems. And quantum computers take the role of solving even more complex, which even supercomputers are not able to solve. Do you think that there's some chance of quantum computers being crashed? Or crashing of quantum computing, or some problem that exists?
The underlying, like about crashing. Yes, of course, as I said before, they have a lot of chance of crashing. Because when you look at it, let's say we use a photon to make a quantum computer or a quantum supercomputer. There are photons all around us. There are photons coming from this light bulb. And even if one gets into that, the entire system will collapse. So the unreliability here is an absolute big factor. And that's why I think, due to the very fundamental nature of quantum computers, we will not be seeing fully quantum computers. Because let's say there's a fully quantum computer on your desktop, there's a small hole, light gets in from the outside, the entire system, boom, gone. Isn't that a terrible kind of technology to have? Yeah. That's why we have these right now in extremely regulated, controlled environments. Not one single qubit comes near, not one single electron comes near, or a nucleus, or a neutron. We have to keep a very shielded environment to prevent the entire system from crashing. One qubit crashes, the other qubit crashes, next thing you know, all 100 qubits are crashing. So it's not like our computers here, classical computers, you have to throw them on the top of a building to break. These just one atom, entire system goes down. That's why I think that we won't see a fully quantum computer commercialized any time. The very fundamental nature, even in 1,000 years, I don't think we'll find a fully quantum computer due to the very unreliable nature of it. Fundamental. So it's simply a fundamental con that we have to take. If you want the power, you have to take the unreliability. If you don't have unreliability, you won't have power. So it's a very tricky situation. Maybe if we find something completely new about quantum mechanics, we can solve this problem, but I wouldn't bet on it. Very good question, thank you.
Quantum computers.
You can ask him whatever language.
Quantum computers super just because they possess. Just because they possess.
You can ask him double if you want.
Quantum computers super fast just because they possess great strong calculation speed for even problems. Quantum computers super fast just because they possess great strong calculation speed for even problems.
Are quantum computers super fast just because they
possess great
process great?
strong calculation speed for even problems.
The calculation time.
Yes.
Are they fast only because they can calculate faster?
Yes. They aren't fast just because they can calculate faster. It's because they can calculate more. One qubit can calculate several things at the same time. As I told you, they are in the state of quantum superposition. So they are two things at once. So a qubit cannot calculate faster, meaning the change of qubits state, that is a computer bit can change from 0 to 1 in a set amount of time. The qubit can change from 0 to 1 at the same time. So the calculation speed fundamentally is not any different, but it can calculate more. So it can have one state 0 and 1, it can have one state 0 and 1, it can have 1 being a mix of 0 and 1. So they do not calculate faster, but they calculate more. That is the fundamental nature of why quantum computers are faster. So they calculate more, not faster. At the same time they calculate more, which means they are only fast because they do several calculations in one qubit. Thank you very much. Very good question.
Do you think will all the classical computers will be replaced by quantum computers?
No, absolutely not. As I said here, quantum computers are extremely unreliable, and I think fundamentally, no matter how much time you take in quantum computing research, there is no way to replace classical computers. Maybe other computer systems will come up. That's not my position to say. I am more of a physics man, but no, they will never be replacing, because computers are still getting faster and faster. That is, silicon computers are getting faster and faster. Quantum computers have great impact in the research field. That they may replace supercomputers. But will they replace normal computers? Like, will this be a quantum computer anytime? Will this presentation be on a quantum computer? No, I highly doubt it. Maybe 50 years later, our understanding of science is completely different, maybe then. But so far, I think there is absolutely no chance that they'll be replacing classical computers. Very good question.
I do.
Yes, sir.
Can I ask another question?
Definitely.
In future, the quantum computer may play a bigger role in AR and VR types of games,
Yeah.
and how?
No, they won't. Because I think right now they are like, they serve the role of the processor in a computer. And you know that AR and VR are all graphics card dependent. Maybe we can use quantum computers in AI research to like upscale the output. For instance, this is running on 1024 by 720 or something. If you had a quantum computer in this classical computer, like I suggested, it could upscale this up to 4K, 8K, and that will help you get an AR experience or VR. But there won't be like a quantum console. You won't have like a PS4, but like a quantum PS4. That won't be happening. But what will be happening is there may be a quantum chip inside that headset, maybe like your Oculus Quest. There will be a quantum chip there to upscale this small image up to a big image in a VR field. So yes, there are applications there. Actually, right now many great researchers are doing work in quantum computers in machine learning. So maybe we can use that to upscale an image, and that will be very useful for VR and AR.
Your answers are too small.
Thank you.
Can you say what the extent of quantum computing ability in future for experts?
Could you please repeat the question?
Can you say what will be the extent of quantum computing ability in future for
Yes,
experts?
the extent, okay, I think definitely I can say with 100% confidence that they will be very impactful in the research field. And as I said before, I told you about consumer applications. That is, you as a consumer, 20 years in the future, 40 years in the future, you are an engineer, you are a researcher, how will it impact you? If you buy a computer, is there any quantum computing element? Yes, I think there will be limited potential for quantum computers in the commercial computer field, but they'll always be working in tandem with the silicon computer. I don't think there'll be replacing silicon computers in terms of consumer technology, but in the research field there will definitely be, even now, right now, some research organizations have stopped using supercomputers for some things and replaced it completely with a quantum computer. So in that sense, definitely there is a great extent in the research field which is not very useful to you, but in the engineering field as well, I think it will have a great impact, but mostly it is a research field type thing. But in the future, it will definitely be working in tandem, that is with classical computers, to give them more power. So definitely I think they'll be ubiquitous, that is, you'll see them everywhere, they'll just be a normal technology, they won't be novel to you anymore. Thank you very much, very great question.
Good morning.
Good morning.
Very glad to meet you first. My question is, can you explain why quantum computing is so fragile?
Yes, quantum computing is so fragile because of the fragility of the state of quantum superposition. Here, as I said, if this is a quantum particle, and if I flip the coin, eventually it will come down and it will be either one or the other. So once I flip it and it's in my hand, it's either heads or tails. So the superposition, while it's in the air, is fragile because of gravity. Gravity is pulling us down. Quantum systems don't have gravity. That's a whole different can of worms. Quantum gravity, that's another thing. You might not read upon. If anyone is curious about quantum mechanics, you should look up quantum gravity. It's an emerging field. Anyway, the state of superposition is so fragile because if anything comes near it, if any particle, one photon or one nucleus or one neutron, anything, even a particle of air, particle of anything comes near it, it's immediately gone. Immediately the whole quantum computer collapses. So that is the problem right now. Anything, it's not a matter of this coin to come down, it needs to be pulled down by gravity. But imagine if just one ray of light hit this coin and it vanished. That is the equivalent with qubits and with the state of quantum superposition. It's because, fundamentally, before we used to think, that is in the times of Schrodinger, we used to think that it was observer based. That is, when we observed it, the superposition collapsed. But now we find out that if anything else interacts with it, it collapses. Because we are also made up of quantum particles. We are made up of atoms and nucleuses and neutrons and so on and so forth. And if we interact with it, it collapses because we are also a quantum particle. We are a bunch of quantum particles. But now we realize that if any quantum particle collides with it, the wave function of the qubit collapses and it becomes practically useless to us. So that is why it's fragile. Because superposition is fragile, quantum computers are fragile. And we can't localize it either. Because all the qubits are connected, one qubit goes, all the qubit goes. And if you want to disconnect it, it's useless as well. So it's either way a very tough break in terms of quantum computing reliability. Fundamentally, it's unreliable. There's really nothing we can do about it unless we change the laws of physics. So thank you very much. Very good question.
First of all, hello and congratulations for your work, and it was a very nice seminar. So my question is, do we have the ability to back ourselves if the quantum computing with the ability has something to defeat the modern cryptography with the ability it has right now? And is this just an opportunity or the chaos? No, it's do we have the ability to back ourselves up if quantum computing with the ability has
you back up consciousness?
Yeah, modern cryptography, it has the ability to.
Yeah, I think definitely quantum computing can be used to map out the human mind. Right now there are two approaches to backing up human consciousness. I'm sure you've seen this in movies, books, all kinds of fiction. We back up our consciousness to the cloud, and I think quantum computing won't do anything special in that sense, but it will definitely help us out because there are two approaches to backing up your consciousness. Either you make a perfect model of your brain, that is, you model every single atom in there and you replicate it perfectly in terms of computer program, or you have to figure out how the brain works and program the brain in without scanning it. But in both of these cases, the quantum computer will give us a processing power to run the human brain. It can't store the human brain. Of course, we need a silicon computer for that. I'm not sure about quantum storage. Even though it can store information, it's not really great in that. But I think to run the human brain, quantum computing definitely will give us the processing power to run a human brain. Because right now our computers are maybe 1/10 as powerful as the human brain, our greatest supercomputers. And maybe in the future, quantum computers will have enough processing power to run a brain, enough processing power to scan a brain, and enough processing power to program a brain. So definitely post very interesting question. I hadn't thought about this. Very great question. Thank you
And
very much.
also I have one more question, sorry for that. So as you claim that Google claim it has just 53 qubits,
Yes.
as you claim, I think so that's a psychomorph processor they
Yes,
created.
yeah.
Can you explain something about that psychomorph processor?
Yes. The Superconducting processor is also a superconducting processor. It has 53 qubits. It has been developed by Google. It's not Google's latest model because they have right now I think the most famous quantum processor is the IBM Eagle with 127 qubits. Up next I think somewhere down the line 1024 qubits. They have an unnamed processor. And Google right now they have a sycamore processor. I think I have a photo of it. I showed a photo of it in the Bishop Weaver lecture. So a sycamore processor has been made by Google. It has 53 qubits. It has a superconducting circuit. And right now, just for the small chip, I think you saw a photo. It's only this big or so. But just to cool this chip and to keep the qubits from collapsing, they need a computer the size of this row. So just to keep this little chip cool. But I think in the future that would go down. Actually, I read press release or something by Google saying that they're mostly working rather on improving the qubits, but to make the qubits more efficient. So how can we squeeze the most out of 53 qubits? Because as I said, the more qubits you add, it's just more trouble, more unreliability, more cooling issues. But if we extract the most power out of these 53 qubits, maybe it can be as powerful as say 100 qubits. So I think that is what Google is doing right now. But right now I think IBM has the edge in terms of qubits and in terms of, I don't know, I think they are more focused on quantum computing research. Google is more doing it just as a backup in case quantum computing becomes something big. Thank you very much for the question. That's it? Yeah, very good questions. Actually, a lot of very good questions from the audience here. And that's exactly what I expected. So I came very prepared. I studied a lot of things. I studied a lot of things about the Anna University Trichy syllabus. I studied all your syllabus, so I know what you studied. I omitted a lot of parts from my lecture because we already studied about them. So exactly what I expected. A wonderful performance from you today, even more than me. Great questions.
Thank you to Qubit for a great lecture and sharing your deep knowledge with us and answering our questions.